Hey everyone, welcome back to the channel. Before we start, I need you to do something for me. Look up at the sky tonight. See that beautiful, peaceful moon glowing up there? Yeah, that thing. That serene celestial body that poets write about and lovers gaze at. I'm about to completely destroy your perception of it. Because what I'm about to tell you will make you realize that the moon, our closest neighbor, is actually far more dangerous and terrifying than Mars could ever be. I know what you're thinking. Wait, what? Mars. The planet with the deadly radiation and toxic soil. The one that's millions of miles away. That Mars is less dangerous than the moon. Yes. Exactly. And by the end of this video, you'll understand why astronauts who've been to the moon have called it the most hostile place they've ever encountered. You'll learn why some of them refuse to talk about their experiences. And you'll discover the hidden dangers lurking on the dusty gray surface that make Mars look like a vacation resort in comparison. But here's the thing that'll really blow your mind. We're planning to go back there. Soon. And the dangers waiting for us haven't gone anywhere. They've been sitting there, waiting, for over 50 years. So stick around, because what you're about to hear will change the way you look at the moon forever. And trust me, you'll want to hear the part about what happened to the astronauts who breathed in moon dust. That story alone is absolutely terrifying. Part 1. The deceptive appearance. Let's start with the basics, because understanding why the moon is so dangerous requires us to first understand what the moon actually is. And I promise you, it's not what you think. When we look at Mars, we see a planet that screams danger. It's red. It looks angry. It's called the Red Planet for a reason. Scientists talk about its harsh environment, its dust storms that can engulf the entire planet, its thin atmosphere that offers zero protection from radiation. When we think about Mars, we think about danger. Our brains are wired to see it as a threat. But the moon? The moon looks peaceful. It's bright. It's beautiful. It's been humanity's companion since the dawn of time. We've written songs about it, worshipped it, used it to mark time and seasons. The moon feels familiar. Safe, even. This is the moon's first and most dangerous trick. It lulls you into a false sense of security. See, Mars is about 140 million miles away from Earth at its closest. The moon? Just 240,000 miles. That's nothing in cosmic terms. You could drive that distance in about 6 months if cars could drive in space. The moon is right there. It's close. It's convenient. And that proximity is exactly what makes it so dangerous, because it tricks us into thinking we understand it. But here's the reality that astronauts discovered when they actually landed there. The moon is one of the most hostile, deadly, and downright terrifying places in our solar system. And unlike Mars, which we've only sent robots to, we've actually sent humans to the moon. 12 people have walked on its surface. And what they found there still haunts some of them to this day. Before we go deeper, let me ask you this. Have you ever wondered why we haven't been back to the moon since 1972? It's been over 50 years. We have technology now that makes the Apollo computers look like calculators. We have better rockets, better materials, better everything. So why haven't we returned? The official answer is money and priorities. But some of the astronauts who went there have hinted at something else. They talk about the moon with a kind of respect that borders on fear. They describe it as magnificent desolation, a phrase Buzz Aldrin used. Magnificent. But desolate. Beautiful. But deadly. And they're absolutely right. Part 2. The dust that shouldn't exist now. Let's talk about something that sounds completely harmless. Dust. Just dust. Tiny particles. How dangerous could dust possibly be, right? Moon dust, or lunar regolith as scientists call it, is nothing like Earth dust. Nothing like it at all. And this is where our first major danger reveals itself. This is the danger that took NASA by complete surprise. This is the danger that nearly killed several astronauts without them even realizing it until it was almost too late. Here's what you need to understand. On Earth, dust particles are smooth. Wind and water have been tumbling rocks and grinding them down for billions of years. By the time something becomes dust on Earth, it's been weathered and eroded so much that the particles are rounded and smooth. You can breathe Earth dust. It's not great for you, but it won't kill you immediately. Moon dust. Completely different story. The moon has no wind. No water. No atmosphere. Nothing to erode those particles. When meteors slam into the moon's surface at thousands of miles per hour, they shatter rocks into microscopic shards. And those shards stay sharp. Incredibly sharp. We're talking about particles that are sharper than broken glass, sharper than razor blades. Under a microscope, moon dust looks like a field of tiny knives. Now imagine breathing that in. Harrison Schmitt, the geologist on Apollo 17, was the first person to have an allergic reaction to moon dust. After his moonwalk, he came back into the lunar module covered in the stuff. It was everywhere. On his suit, in the air, floating around in the zero gravity. And he breathed it in. He described it as experiencing something like hay fever, but worse. His nose stuffed up immediately. His throat felt scratchy. His eyes watered. He felt like he couldn't breathe properly. And remember, this was in the tiny, enclosed space of the lunar module. There was nowhere to go. No fresh air to breathe. He was trapped with this toxic dust for hours. But here's the terrifying part. The symptoms went away after a while, and everyone thought it was no big deal. Just an allergic reaction, right? Wrong. We now know that moon dust is incredibly toxic to human lung tissue. Those microscopic glass shards don't just irritate your lungs. They slice them up. They embed themselves in the delicate tissue of your alveoli, the tiny air sacs where oxygen enters your bloodstream. Once in there, they're almost impossible to remove. Studies done on simulated moon dust have shown that it can cause something called silicosis, a deadly lung disease. But it's actually worse than regular silicosis because moon dust particles are so much sharper and so much finer. They can penetrate deep into your lungs, deeper than almost any Earth-based particle. And here's the kicker. Moon dust also contains tiny particles of iron. Not iron oxide like rust. Pure iron. Because there's no oxygen on the moon to oxidize it. When that pure iron gets into your lungs and then comes into contact with the moisture there, it starts to oxidize inside your body. It rusts. In your lungs. Think about that for a second. Breathing in moon dust means breathing in thousands of microscopic razor blades that then start rusting inside your lungs. But wait. It gets worse. Moon dust isn't just a breathing hazard. It's a technological nightmare. Remember how I said it's everywhere? The Apollo astronauts couldn't keep it out of anything. It got into their equipment. It got into the seals of their suits. It scratched their helmet visors so badly that some astronauts had trouble seeing by the end of their moonwalks. It jammed zippers. It contaminated their food. It got into the electronics. One astronaut's suit developed a leak because moon dust had abraded the seal. If that leak had gotten bigger, he would have been exposed to the vacuum of space. He would have died. Right there on the moon. All because of dust. And here's something that'll really make your skin crawl. Moon dust is electrostatically charged. Because there's no atmosphere to discharge it, and because it's constantly being bombarded by solar radiation, it builds up a static charge. That means it actively clings to things. It jumps onto surfaces. It's attracted to your suit, your equipment, everything. The astronauts described how it would leap up from the ground when they walked. Like it was alive. Like it was trying to get onto them. They couldn't brush it off. They couldn't shake it off. It stuck to everything like magnetic glue. Now imagine trying to build a moon base with this stuff everywhere. Imagine trying to grow food, repair equipment, or simply live day-to-day when this toxic, razor-sharp, electrostatically charged nightmare dust is coating everything you own and getting into every breath you take. Mars has dust storms, sure. But Martian dust is weathered. It's been eroded by the thin atmosphere for billions of years. It's still dangerous, don't get me wrong. But it's nowhere near as immediately lethal as moon dust. And this is just the beginning of our list of lunar horrors. Because the dust. The dust is actually one of the less terrifying problems. Part 3. The deadly vacuum. Let's talk about atmosphere. Or rather, the lack of it. Because this is where the moon's true face starts to show itself. Mars has an atmosphere. It's thin. Really thin. About 1% of Earth's atmospheric pressure. But it's there. It provides some protection from radiation. It creates some temperature stability. It even allows for weather. Those famous Martian dust storms I mentioned. Those happen because Mars has an atmosphere. The moon. Nothing. Absolute nothing. A vacuum so perfect that scientists on Earth can't even recreate it in laboratories. And that vacuum is constantly trying to kill you in ways you probably haven't even thought about. Let me paint you a picture. You're standing on the moon. You're wearing your spacesuit, of course. You're fine. You're safe. But then you notice a small tear in your glove. Maybe from that razor-sharp dust we just talked about. Maybe from snagging it on a rock. Just a tiny tear. Barely visible. What happens next is not what you've seen in movies. You don't explode. You don't instantly freeze. Those are Hollywood myths. What actually happens is somehow more terrifying because it's slower. More insidious. The air starts rushing out of your suit. You feel it going. You hear the hiss. You have maybe seconds to react before the pressure drops enough that your blood starts to boil. Not from heat. From the lack of pressure. Water boils at room temperature in a vacuum. Your lungs are the first to go. If you hold your breath, trying to keep your air in, your lungs will rupture. The pressure difference is too much. You have to exhale. You have to let the air out. But once you do, you're breathing vacuum. Your lungs collapse. The moisture on your tongue and in your mouth begins to boil. Your eyes dry out in seconds. You lose consciousness in about 15 seconds. Brain death follows shortly after. You're dead in about 2 minutes. And the worst part? You're aware for most of it. You know what's happening. You feel it happening. And there's nothing you can do to stop it. This nearly happened several times during the Apollo missions. Suits got damaged. Seals were compromised. The astronauts came terrifyingly close to experiencing exactly this scenario. They survived through a combination of quick thinking, redundant systems, and pure luck. But here's what makes the moon's vacuum even more dangerous than Mars's thin atmosphere. On Mars, the atmospheric pressure is low, but it's not zero. If your suit fails on Mars, you have a slightly better chance of survival. The pressure difference isn't as extreme. You might have a few extra seconds to react. Your equipment might work slightly better. On the moon. Zero margin for error. None. Any failure is immediately catastrophic. And remember, we're planning to send people back there. To live there. For months or even years. Think about that. Think about spending months in an environment where a tiny tear in your suit means certain death, and that tear can happen at any moment from dust you can't see, can't control, and can't avoid. But the vacuum isn't just a direct threat to human life. It makes everything harder. Every single thing. Want to repair something outside? You can't just run out there quickly. You need to put on a full spacesuit. That takes time. Time you might not have if something is failing. On Mars, the same is true, but at least you can move around more easily in the slightly higher pressure. Your suits can be a bit less bulky. A bit more flexible. Want to bring samples inside to study? On the moon, you need an airlock. A perfect airlock. Because any contamination, any loss of pressure, could kill everyone inside. The Apollo astronauts had to be incredibly careful about this. They had procedures within procedures within procedures, all designed to make sure that the vacuum stayed outside. And here's something that might not seem obvious at first. The vacuum affects radiation. We'll talk more about radiation in a minute, but here's the preview. Mars's thin atmosphere provides some shielding from cosmic rays and solar radiation. Not much, but some. The moon's vacuum. No shielding at all. 0. Every single particle of radiation that comes screaming through space hits the moon's surface at full force. But before we get to radiation, I need to tell you about another consequence of the vacuum. One that nearly drove some of the Apollo astronauts insane. The silence. On Earth, we're used to sound. Even in the quietest places, there's always some sound. Air moving. Insects. Distant traffic. Something. On Mars, with its thin atmosphere, you'd still be able to hear things. Your equipment. Your breathing. Muffled sounds through your suit. On the moon, in the perfect vacuum, there is no sound. None. When you're outside your habitat, the only thing you can hear is yourself. Your breathing. Your heartbeat. The mechanical sounds of your suit transmitted through your body. That's it. Several Apollo astronauts have talked about how unsettling this was. How alien it felt. How it messed with their minds. They described feeling isolated in a way they'd never experienced before. Cut off not just from Earth, not just from other people, but from the very concept of sound itself. Imagine living like that. 4 months. The psychological toll would be immense. Part 4. Temperature swings from hell. Now let's talk about temperature. Because this is where the moon really shows its teeth. You know how hot deserts are during the day and how cold they get at night. Death Valley can hit 130 degrees Fahrenheit during the day and drop to 50 degrees at night. That's an 80-degree swing, and it's enough to kill you if you're not prepared. The moon makes Death Valley look like a thermostat malfunction. During the lunar day, which lasts about 2 Earth weeks, temperatures on the moon's surface reach 260 degrees Fahrenheit. That's hot enough to boil water. Hot enough to melt some plastics. Hot enough that exposed human skin would burn in seconds. During the lunar night, which also lasts 2 weeks, temperatures plummet to negative 280 degrees Fahrenheit. That's colder than the surface of Pluto. Colder than liquid nitrogen. So cold that some materials become brittle and shatter. That's a temperature swing of 540 degrees. 540 degrees. In a single location. Over the course of a month. Let me put that in perspective. The difference between the hottest temperature ever recorded on Earth and the coldest is only about 280 degrees. The moon exceeds that by almost double. In one spot. Just by waiting for night to fall. Mars has temperature swings too. They can be significant, dropping from about 70 degrees Fahrenheit during the day to negative 100 at night. That's roughly 170 degrees, which is definitely dangerous. But it's nowhere close to the moon's extremes. Why is the moon so much worse? 2 reasons. First, no atmosphere. On Mars, the thin atmosphere acts as a buffer. It absorbs some heat during the day and releases it slowly at night. It's not much, but it's something. The moon has nothing. No buffer. No moderation. Just direct exposure to the sun for 2 weeks, then direct exposure to the frozen void of space for 2 weeks. Second, the length of the day. Mars's day is about 25 hours, similar to Earth's. So the temperature swings happen over a predictable, manageable cycle. You get warm during the day, cool at night, warm again, cool again. Your equipment can handle that. Your body can adapt to that rhythm. The moon's day is 2 Earth weeks long. 2 weeks of being roasted. 2 weeks of being frozen. There's no daily cycle to adapt to. No rhythm. Just extremes that last for weeks at a time. Now imagine trying to build a habitat on the moon. Your structure needs to withstand both extremes. It needs to keep you cool during the day without using too much power. It needs to keep you warm at night without using too much power. And remember, solar panels only work during the day. During the 2-week lunar night, you're running on batteries. Just batteries. For 2 solid weeks. The Apollo missions dodged this problem by only landing during lunar dawn, when temperatures were more moderate. They were there for a few days at most. They could manage. But a permanent base? That's a completely different challenge. Your habitat would need incredible insulation. It would need redundant heating and cooling systems. It would need power systems that could last through 2 weeks of darkness. And all of this equipment would need to survive the temperature swings itself. Metal expands when hot and contracts when cold. Over small temperature ranges, this is manageable. Over 540-degree ranges, materials fail. Seals crack. Joints separate. What was airtight at 260 degrees might have gaps at negative 280 degrees. And remember what we said about the vacuum. Any gap is potentially lethal. The Apollo astronauts noticed this. Their equipment behaved differently as temperatures changed. Things that worked fine at first would fail later. Mechanisms would jam. Electronics would malfunction. They were only there for a few days and they experienced significant problems. Now multiply that by months or years. But here's what really makes the moon's temperature problem so much worse than Mars's. On Mars, you can plan around the daily cycle. You know that in roughly 25 hours, things will cool down or warm up. You can time your activities. Schedule your work. Manage your resources. On the moon, you're dealing with these massive, slow-moving waves of extreme temperature. 2 weeks of heat. 2 weeks of cold. 2 weeks of heat. 2 weeks of cold. Forever. And in the permanently shadowed craters near the moon's poles. Places where the sun never shines. Temperatures stay at negative 400 degrees Fahrenheit. That's colder than Pluto. That's colder than the boiling point of oxygen. Some of these craters are the coldest places in the entire solar system. Why does this matter? Because these same craters are where we think water ice is located. Water we want to mine for drinking, for breathing, for making rocket fuel. To get that water, we'd need to send equipment and possibly people into these craters. Into temperatures so cold that most materials become brittle and fail. It's like the moon is testing us. Dangling valuable resources in the most inhospitable locations possible, just to see if we're clever enough and tough enough to get them. Mars, for all its dangers, doesn't play these games. Its temperature extremes are harsh but manageable. Its day-night cycle is human-friendly. The moon. The moon is actively hostile. Okay, now we need to talk about radiation. And this is where things get really scary. Because unlike dust that you can see, or temperature extremes that you can feel, or vacuum that you can hear rushing out of your suit, radiation is invisible. Odorless. Tasteless. You can't detect it with your senses. And by the time you realize you've been exposed, the damage is already done. Let's start with Earth, just for context. We're protected by two things. First, our atmosphere, which blocks most radiation from space. Second, our magnetic field, which deflects charged particles from the solar wind. These two shields work together to make Earth's surface a relatively safe place to live. Mars has a thin atmosphere, as we've discussed. It provides some protection. Not much, but some. Mars used to have a magnetic field, but it died billions of years ago. So Mars gets hit with more radiation than Earth, but its atmosphere still helps. The moon. No atmosphere. No magnetic field. Nothing. Every bit of cosmic radiation that comes screaming through space hits the moon at full force. Solar flares. Cosmic rays. Galactic cosmic radiation. All of it. No protection. No shielding. Nothing between you and the raw fury of the universe. Let me explain what this means in practical terms. On Earth, the average person receives about 3 millisieverts of radiation per year from natural sources. That's background radiation from rocks, from the sun, from space, from radon in the air. 3 millisieverts. That's our baseline. On the International Space Station, which is in low Earth orbit and still partially protected by Earth's magnetic field, astronauts receive about 150 millisieverts per year. That's 50 times more than on Earth. Astronauts who spend 6 months on the ISS come back with a measurably increased risk of cancer. Not a huge increase, but it's there. It's real. On the moon. Estimates suggest around 380 millisieverts per year. Some studies say it could be even higher. That's over 100 times the radiation dose you'd get on Earth. That's more than double what astronauts get on the ISS. Now, 380 millisieverts per year might not sound immediately deadly. And it's not. You wouldn't die instantly from radiation on the moon. But here's the thing. That's the average. Averages can be deceiving. Most of the time, radiation levels on the moon are at that baseline level. Dangerous, but manageable with proper shielding. But then the sun burps. Solar flares. Coronal mass ejections. The sun isn't a steady, calm ball of fire. It's violently active. It throws off massive amounts of radiation at unpredictable intervals. Sometimes multiple times a day. Sometimes not for weeks. We can't predict them accurately. We can see them happening, but by the time we see them, the radiation is already on its way. During a major solar event, radiation levels on the moon can spike to thousands of millisieverts per hour. Not per year. Per hour. If you're outside during one of these events, you could receive a lethal dose in minutes. If you're in a habitat with minimal shielding, you might still receive enough radiation to cause acute radiation sickness. Nausea, vomiting, diarrhea, hair loss, immune system damage, increased cancer risk. All from a single event. The Apollo astronauts got incredibly lucky. Between Apollo 11 in 1969 and Apollo 17 in 1972, there were no major solar events during any of the moonwalks. If there had been, those astronauts would have died. Their suits provided almost no radiation protection. Their lunar modules had thin aluminum walls. A major solar flare would have cooked them. In August 1972, between Apollo 16 and Apollo 17, there was a massive solar event. One of the largest on record. If astronauts had been on the moon during that event, they would have received a lethal dose of radiation. They would have died either on the moon or shortly after returning to Earth. We got lucky. Pure luck. That's all that saved them. Now we're planning to go back. To stay for extended periods. And the solar cycle is still there, still active, still unpredictable. Every astronaut on the moon will be gambling with their life every single day, hoping that the sun stays calm. But solar flares aren't even the worst of it. At least with solar flares, you get some warning. A few minutes. Maybe an hour if you're lucky. Enough time to get inside and hope your shielding is enough. Galactic cosmic rays are different. These are particles accelerated to nearly the speed of light by distant supernovas and other cosmic events. They're rare, but they're constantly bombarding the moon. And they're incredibly energetic. So energetic that they can punch right through spacecraft walls, right through your body, causing damage to your DNA. Every hit from a high-energy cosmic ray is like playing Russian roulette with your chromosomes. Most of the time, nothing happens. Your body repairs the damage. But sometimes, the damage sticks. Sometimes, it causes a mutation. Sometimes, that mutation becomes cancer. Years later. Decades later. The Apollo astronauts are dying of heart disease and cancer at higher rates than the general population. Studies have linked this to their radiation exposure during their missions. They were only on the moon for a few days each. Imagine living there for months or years. Now here's where Mars actually has an advantage. Mars's thin atmosphere provides some shielding. Not a lot, but some. Enough to reduce radiation levels to about 230 millisieverts per year on the surface. That's still dangerous. That's still much worse than Earth. But it's measurably better than the moon. Plus, Mars has geography. It has caves. It has lava tubes. It has cliffs and valleys. You can dig into the Martian soil and use it as shielding. Martian regolith is thick and covers large areas. You can pile it on top of your habitat and create effective radiation shielding. The moon has some of these features too, sure. There are lava tubes on the moon. There are craters. But the moon is much smaller than Mars. It has less surface area to work with. Less variety in terrain. And the moon's regolith, while it can be used for shielding, is that toxic, razor-sharp dust we talked about. Handling it, moving it, piling it up is incredibly difficult and dangerous. Every solution to the moon's radiation problem creates new problems. Build thick walls. They're heavy, hard to construct, and you need to transport the materials. Use moon dirt for shielding. Now you're dealing with toxic dust contamination. Go underground. Now you're digging into unknown territory with unknown hazards, still dealing with dust, and creating structural challenges. There's another aspect to radiation that people don't often think about. Electronics. Radiation doesn't just harm people. It damages electronics too. High-energy particles can cause bit flips in computer memory. They can permanently damage microchips. They can degrade solar panels over time. The electronics we use in space are specially hardened against radiation. They're more expensive, heavier, and often less capable than commercial electronics. And even they fail eventually under constant bombardment. On a moon base, every computer, every sensor, every piece of electronic equipment would be slowly dying from radiation exposure. You'd need constant maintenance, constant replacement. Every EVA suit has computers in it. Every rover. Every life support system. All of them slowly degrading, all the time, from radiation you can't see or feel. Mars has this problem too, but to a lesser degree. The radiation there is lower. Electronics last longer. Maintenance cycles can be longer. The moon gives you no breaks. No mercy. Every single day, radiation is trying to kill you and destroy your equipment. And there's nothing you can do to stop it. Only delay it. Part 6. The deafening silence and psychological horror. We touched on this briefly before, but now we need to really dive into it. Because the moon doesn't just threaten your body. It threatens your mind. Humans are social creatures. We evolved in groups. We need other people. We need interaction. We need stimulation. The longest anyone stayed on the moon during Apollo was about 3 days. That's a long weekend. We're now talking about stays of months or years. Let's start with isolation. Mars is far away. Really far away. Communication with Earth has a delay of anywhere from 3 to 22 minutes, depending on orbital positions. That's significant. You can't have a real-time conversation. But you can still communicate. You can send messages. You can receive responses the same day. The moon is close. Only about 1.25 light seconds away. Communication is basically instant. You can have real-time conversations with Earth. That sounds like an advantage, right? In some ways it is. But it's also a psychological trap. Being on Mars, you'd know you're isolated. You'd accept it. You'd adapt to the delay. Your brain would adjust to the reality that Earth is truly far away. You'd build your own community with the other people on Mars. You'd become, in a sense, Martian. On the moon, Earth is right there. You can see it. It's huge in the sky. You can talk to people on Earth in real time. But you can't touch it. You can't go there. You can't breathe its air. You can't feel its gravity. You're so close, but completely unreachable. Several psychologists have suggested that this might be harder to handle than true isolation. It's like watching your family through a window but never being able to open the door. The proximity makes the separation more painful, not less. And then there's the moon itself. Apollo astronauts have described the moon as beautiful but dead. Utterly dead. There's no weather. No erosion beyond the incredibly slow process of micrometeorite impacts. Footprints they left in 1969 are still there today, unchanged. Will be there for millions of years. Everything on Earth changes. Constantly. Wind blows. Water flows. Plants grow. Animals move. Even in the most barren deserts on Earth, there's some change. Some life. Some movement. The moon is static. Frozen. Dead. The landscape doesn't change. The sky is black. The Earth hangs in the same spot, going through its phases. That's it. That's all the variety you get. Living there would be like living in a photograph. A high-resolution, incredibly detailed photograph that you're trapped inside. Day after day. Week after week. Month after month. Some Apollo astronauts reported feeling deeply unsettled by this. By the absolute stillness. The permanence. The deadness. And they were only there for days. Now add in the dangers we've already discussed. The constant threat of dust. The vacuum waiting to kill you. The radiation bombarding you. The temperature extremes. Living on the moon would be a state of perpetual alertness. Perpetual stress. You could never fully relax. Never fully let your guard down. One mistake, one moment of inattention, could be fatal. Compare this to Mars. Mars is more dynamic. It has an atmosphere, which means weather. Dust storms. Clouds. Frost. The sky changes color throughout the day, from butterscotch to blue to pink. The landscape is varied. Mountains. Valleys. Canyons. Potential signs of ancient rivers and lakes. Mars feels more alive. More dynamic. More interesting. Psychologically, this matters. A lot. And there's something else. Something the Apollo astronauts have talked about that's hard to quantify but deeply disturbing. The sense of wrongness. Multiple astronauts have described feeling like they didn't belong on the moon. Like they were somewhere they shouldn't be. Some described it as a feeling of being watched, though there was nothing there to watch them. Others talked about an oppressive sense of hostility, as if the moon itself didn't want them there. These are trained professionals. Test pilots. Engineers. Scientists. Not people prone to superstition or flights of fancy. And yet multiple independent accounts describe similar feelings. Alan Bean, who walked on the moon during Apollo 12, said he occasionally felt fear on the moon in a way he never felt during his entire career as a fighter pilot and test pilot. Not fear of the known dangers like equipment failure, but a deeper, more primal fear that he couldn't explain. Edgar Mitchell, Apollo 14, reported having a profound experience on the moon that he spent the rest of his life trying to understand. He described feeling connected to the universe in a way that was both beautiful and terrifying. Buzz Aldrin has talked about the psychological toll of his moon experience, though he's been less specific about the details. But his struggles with depression and alcoholism after Apollo 11 are well documented. Is the moon haunted? No, of course not. But there's something about being in such an utterly alien, hostile environment that affects the human psyche in ways we don't fully understand. The human brain didn't evolve to handle the moon. We evolved for Earth. For blue skies and breathable air and the sounds of wind and water and life. The moon offers none of that. It's the antithesis of everything our brains expect. And spending extended time there would put immense psychological strain on anyone, no matter how well trained or prepared. Mars, while still alien, is at least dynamic. It has weather patterns your brain can track. A day-night cycle you can adapt to. An environment that changes in predictable ways. It's still incredibly harsh, but it's not dead in the way the moon is dead. And here's one more psychological factor that people don't think about. Escape. If something goes catastrophically wrong on Mars, you're stuck there. It takes months to get back to Earth. There's no quick escape. But psychologically, you accept this before you go. You know the deal. You make peace with it. If something goes catastrophically wrong on the moon, Earth is right there. 3 days away. You can see it. You can talk to people there. But if your rocket is damaged, if your life support is failing, if you're dying from radiation or dust inhalation or any of the other countless ways the moon can kill you, those 3 days might as well be 3 years. You're watching Earth, your home, your salvation, right there in the sky. And you can't reach it. The psychological torture of that situation would be immense. Part 7. Micrometeorites, death from above. Let's talk about something most people don't even know is a threat. Micrometeorites. Tiny rocks screaming through space at thousands of miles per hour. On Earth, we don't think about them because our atmosphere burns them up. We see them as shooting stars. Pretty. Harmless. Romantic even. On the moon, they're bullets. Space is full of debris. Tiny bits of rock and metal, leftovers from the formation of the solar system, fragments from asteroid collisions, dust from comets. This stuff is everywhere. And it's moving fast. Really fast. On Earth, when this debris enters the atmosphere, it's moving at speeds of anywhere from 25,000 to 160,000 miles per hour. The atmosphere creates friction, which creates heat, which vaporizes the debris before it reaches the ground. The few that make it through are slowed down enough that they're no longer dangerous. The moon has no atmosphere. These micrometeorites hit the surface at full speed. And they don't just hit the surface. They hit anything on the surface. Including you. Now, space rocks larger than a pea are actually pretty rare. The chances of being hit by one are tiny. But here's the thing. You don't need to be hit by something large to be in serious trouble. Micrometeorites the size of a grain of sand hit the moon constantly. Every day. Every hour. Thousands of them. And at the speeds they're traveling, even a grain of sand has the kinetic energy of a bullet. Think about that. A grain of sand. Moving at 50,000 miles per hour. Hitting your spacesuit. NASA studied this extensively before Apollo. They were worried about it. Really worried. They designed the spacesuits with multiple layers specifically to protect against micrometeorite impacts. The outer layer of an Apollo spacesuit was tough. Really tough. Kevlar-like materials. Multiple redundant layers. And you know what? Those suits got hit. Multiple times. The astronauts would come back and find tiny holes in the outer layers of their suits. Not big enough to puncture through completely, but big enough to be concerning. If one of those micrometeorites had hit just right, at just the right angle, with just the right amount of energy, it could have punched through. And that would have been it. Game over. The astronauts knew this. They talked about it. They talked about hearing tiny impacts on their suits. Little tinks and taps. Each one a reminder that they were being bombarded with projectiles moving faster than bullets. Each one a reminder that their lives depended on a few layers of fabric and some really good engineering. Now imagine building a base on the moon. You need habitats. You need rovers. You need equipment sitting outside. All of it being constantly sandblasted by micrometeorites. Over time, this creates damage. Erosion. Pitting. Weakening of materials. Your habitat's walls need to be thick enough to withstand not just one impact, but thousands. Millions. Over years. The solar panels you depend on for power. They'll get pitted and scratched, reducing their efficiency over time. The windows you need to see outside. They'll get frosted and damaged. The seals and joints in your equipment. They'll degrade faster than on Earth because there's no atmosphere to slow down or burn up the debris. And here's the really scary part. These impacts are random. Unpredictable. You can't see them coming. You can't dodge them. You just have to hope that your equipment is tough enough and that you're not in the wrong place at the wrong time. On Mars, the atmosphere provides protection. Not complete protection, but significant protection. Micrometeorites slow down. They burn up. They lose energy. Mars still gets hit by space debris, but the impacts are less severe. Materials last longer. Equipment degrades more slowly. The moon. No protection. Every single piece of debris hits at full cosmic velocity. It's like living in a shooting gallery where you can't see the guns and the bullets never stop. And there's more. When micrometeorites hit the moon's surface, they don't just disappear. They explode. They vaporize rock. They create ejecta. Tiny particles that get thrown up into space at high velocity, only to fall back down somewhere else. This means that even if a micrometeorite doesn't hit you directly, the debris from its impact somewhere else might. The moon is essentially recycling danger. Every impact creates more projectiles, which create more impacts, which create more projectiles. It's been doing this for billions of years. The Apollo astronauts noticed their equipment getting damaged in ways they couldn't explain. Scratches appearing overnight. Pitting on surfaces. They attributed some of it to the dust, but some of it was almost certainly from micrometeorite impacts and secondary ejecta. Living on the moon long-term means accepting that your equipment, your habitat, and potentially your body are being slowly eroded by invisible projectiles from space. There's no way to stop it. No way to prevent it. Only to build things tough enough to withstand it and hope that nothing critical gets hit. Now let's talk about something that seems like it should be good news but actually isn't. Gravity. Or rather, the lack of it. The moon's gravity is about 1/6 of Earth's. That means if you weigh 180 pounds on Earth, you weigh 30 pounds on the moon. You can jump 6 times higher. Lift objects 6 times easier. It sounds fun. It sounds like an advantage. It's not. Human bodies evolved in Earth's gravity. Our bones, our muscles, our cardiovascular system, our inner ear balance system, all of it is calibrated for 1 g of gravitational force. Take that away, and things start to go wrong. Quickly. On the International Space Station, astronauts are in microgravity. Essentially 0 g. We know what happens to them. Their bones lose density. Their muscles atrophy. Their cardiovascular systems weaken. They have to exercise for hours every day just to minimize the damage. And even then, when they come back to Earth, they can barely walk for the first few days. Some effects are permanent. The ISS astronauts are in 0 g. What about 1/6 g? Is that better? We don't know. And that's terrifying. We've never had humans in 1/6 gravity for extended periods. The Apollo astronauts were only there for days. Not long enough for significant changes. We don't know if 1/6 g is enough to prevent bone loss and muscle atrophy. We don't know if it's enough to keep your cardiovascular system healthy. We don't know if your balance system can adapt to it without permanent damage. We suspect it's better than 0 g. But we don't know how much better. And we won't know until we try. Until we send people to the moon for months and see what happens to them. That's a huge risk. A massive unknown. You're volunteering to have your body used as an experiment to see if long-term moon living is even viable for humans. And here's the kicker. If it turns out that 1/6 g isn't enough, if people start experiencing significant bone loss and muscle atrophy and cardiovascular problems, there's no quick fix. You can't just turn up the gravity. You can't just come home if your body is too weak to handle the trip. You're stuck there, your body deteriorating, hoping that medical science can figure out a solution before permanent damage sets in. Compare this to Mars. Mars has about 1/3 Earth's gravity. That's twice what the moon has. We still don't know if it's enough for long-term human health, but it's more likely to be adequate. It's closer to Earth normal. Your body would have to adapt less. The stresses would be lower. But the moon's low gravity creates other problems too. Problems with basic tasks. Try to imagine walking with 1/6 gravity. Every step propels you forward and upward more than you expect. Your inner ear is confused because the balance system it evolved over millions of years is suddenly wrong. Apollo astronauts developed a hopping gait because normal walking was inefficient and disorienting. This takes practice. Lots of practice. And even then, you never quite feel natural. Several Apollo astronauts reported that they never fully adjusted to moon gravity, even after days there. It always felt wrong. Off. Uncomfortable. Now imagine doing delicate work in this environment. Trying to repair equipment. Trying to conduct scientific experiments. Every movement has to be recalibrated. Every tool weighs 1/6 what it should. Your muscle memory is useless. Everything is harder than it should be. The low gravity also affects how things behave. Throw a wrench, and it goes 6 times farther than you expect. Drop something, and it falls 6 times slower. Liquids behave strangely. Pouring water from a bottle is different. The arc is different. The splash is different. Everything you learned about how objects move on Earth is wrong. And here's something really disturbing that NASA scientists have studied. The low gravity might affect your immune system. Your body's immune response is tied to gravity in ways we don't fully understand. White blood cells move through your body partly through gravity. Reduce the gravity, and you might reduce your immune system's effectiveness. We've seen hints of this on the ISS. Astronauts get sick more easily in space. They're more susceptible to infections. Their wounds heal more slowly. Is this from zero-G? Or from radiation? Or from stress? Or from all of the above? On the moon, you'd have 1/6 G, plus radiation, plus stress. Your immune system would be under assault from multiple directions. Getting sick on the moon could be much more dangerous than getting sick on Earth, not just because medical care is limited, but because your body might not be able to fight off the infection as effectively. And then there's what happens when you come home. After months or years in 1/6 gravity, your bones are weaker. Your muscles are smaller. Your heart is less efficient. And now you have to handle full Earth gravity. It would be like suddenly weighing 6 times more than you're used to. Your body would be crushed by its own weight. Recovery would take months. Maybe longer. Some effects might be permanent. Your bones might never fully recover their original density. Your cardiovascular system might never be the same. You might have chronic pain or mobility issues for the rest of your life. This is the price of living on the moon. Your body, the one you've had your whole life, would become adapted to a place that isn't Earth. And when you try to return home, your home would reject you. Your own body weight would become a burden. Mars has this problem too, but less severely. Coming home from Mars would still be hard. Your body would still need time to readjust. But the transition wouldn't be as extreme. 1/3 G to 1G is a smaller jump than 1/6 G to 1G. The moon's low gravity is a trap. It seems like a gift. Easier to move around. Easier to lift things. But it's slowly destroying your body in ways you can't feel until it's too late. And once you're adapted to it, Earth becomes a prison of crushing weight. Part 9. No magnetic field, the shield we take for granted. We need to go deeper on something I mentioned earlier. The magnetic field. Or rather, the moon's complete lack of one. Because this isn't just about radiation. This affects everything. Earth's magnetic field is generated by our planet's molten iron core. This field extends thousands of miles into space, creating a protective bubble called the magnetosphere. This magnetosphere deflects charged particles from the solar wind. It prevents them from stripping away our atmosphere. It protects us from massive amounts of radiation. We don't think about it because we can't see it or feel it. But it's there. Always. Protecting us. Keeping us alive. Mars used to have a magnetic field. Billions of years ago, its core was molten and active. But it cooled. The magnetic field died. And over millions of years, the solar wind stripped away most of Mars's atmosphere. What's left is a thin remnant. But at least there's something left. Some protection. The moon never had a strong magnetic field. Its core is small and cooled quickly. It's been defenseless for its entire existence. 4.5 billion years of being blasted by the full force of solar wind and cosmic radiation. What does this mean for humans living there? First, as we discussed, radiation exposure is much higher. But the lack of a magnetic field causes other problems that are less obvious but equally dangerous. The solar wind is a stream of charged particles flowing from the sun. These particles interact with magnetic fields. On Earth, they get deflected. On the moon, they hit the surface. And when they do, they charge the dust. Remember that electrostatically charged moon dust we talked about? The stuff that clings to everything. The reason it's so charged is because of the solar wind. Particles constantly bombarding the surface, transferring their charge to the dust particles. This makes the dust even more dangerous than it would otherwise be. It actively jumps onto your equipment. It's attracted to your suit because your suit has a different electrical potential. You can't brush it off because the electrostatic force is stronger than your brushing. This is a direct result of the lack of a magnetic field. Mars has this problem too, but to a lesser degree because its thin atmosphere provides some shielding from the solar wind. Second, the solar wind creates something called a plasma environment around the moon. During lunar day, the side facing the sun is bombarded with solar wind particles. These create an electrical potential difference between the day side and the night side of the moon. Astronauts walking on the boundary between lunar day and night could potentially experience electrical shocks. Not strong enough to be immediately dangerous, but enough to damage sensitive electronics. Apollo astronauts reported seeing flashes of light when they closed their eyes, probably from charged particles hitting their retinas. Imagine seeing phantom lights every time you blink. For weeks or months. Third, the lack of a magnetic field means there's no protection from coronal mass ejections. These are massive eruptions of plasma from the sun that can engulf Earth's entire orbit. When they hit Earth, our magnetic field deflects most of the particles. We see auroras. Beautiful, harmless auroras. When a coronal mass ejection hits the moon, there's no deflection. No protection. Just a tsunami of charged particles and radiation. If you're on the moon during one of these events, you'd better be deep underground or in a heavily shielded habitat. Otherwise, you're getting a potentially lethal dose of radiation. These events are unpredictable. We can't forecast them more than a few days in advance, sometimes not even that. Living on the moon means living with the constant threat that the sun might throw a cosmic punch at you with no warning. Fourth, and this is subtle but important, the lack of a magnetic field affects navigation. On Earth, we use compasses. They work because of Earth's magnetic field. On the moon, compasses are useless. You need to navigate by landmarks or by GPS, assuming your GPS satellites are working and positioned correctly. This seems minor until you're trying to navigate during the 2-week lunar night. It's completely dark. Your landmarks are invisible. If your GPS fails or if you're in an area without satellite coverage, you're lost. Genuinely lost in a way that's hard to be on Earth, where you can usually find some way to orient yourself. Mars has a weak magnetic field in some regions. Ancient magnetic rocks create local field anomalies. It's not enough for reliable compass navigation, but it's something. You can use magnetic sensors to help orient yourself. The moon. Nothing. Absolute magnetic dead zone. And here's one more thing about magnetic fields that people don't realize. They protect against more than just solar wind. They protect against high-energy cosmic rays. These particles are moving so fast that atmosphere and rock can barely stop them. But magnetic fields can deflect them, send them curving away. Earth's magnetosphere deflects many of these cosmic rays before they even reach our atmosphere. Mars's thin atmosphere provides some protection. The moon has no magnetic field and no atmosphere. Every cosmic ray that comes screaming in from deep space hits the surface with its full energy. These are the particles that cause the most DNA damage. The ones most likely to cause cancer. The ones most likely to damage your brain and nervous system. And there's absolutely no natural protection from them on the moon. You could build magnetic shielding. Generate artificial magnetic fields around your habitat. But that requires energy. Lots of energy. Constant energy. If your power fails, if your generators break down, the shielding disappears and you're exposed. Living on the moon means living in a place that the universe is actively trying to kill. Not in a malevolent way. Not intentionally. But the forces of nature, the solar wind, the cosmic rays, the micrometeorites, they all pass through the moon's location constantly. Earth's magnetic field turns these forces aside. Mars's thin atmosphere reduces them. The moon just takes the hits. All of them. Forever. Part 10. Water, the resource we need and can't easily get. Let's talk about water. Because humans need water. Desperately. We can survive weeks without food, but only days without water. Any long-term presence on the moon requires a water source. This sounds obvious, but the implications are terrifying. Earth has abundant water. It falls from the sky. It flows in rivers. It fills our oceans. We take it completely for granted. Even in deserts, you can usually find water if you dig deep enough or collect it from the air. Mars has water. We've confirmed this. There's water ice at the poles. There's water trapped in the soil. There's even seasonal liquid brine in some areas. Getting to it would be challenging, but it's there. Accessible. Usable. The moon has water too. Probably. We think. In permanently shadowed craters at the poles. Maybe in the regolith in trace amounts. But here's the problem. Getting to it is incredibly difficult. Using it might be even harder. The water at the lunar poles is in craters that are permanently shadowed. These craters are, as I mentioned before, the coldest places in the solar system. -400 degrees Fahrenheit. To get the water out, you need to go into these craters with equipment that can function at these temperatures. You need to dig through or melt lunar regolith that's frozen harder than concrete. And you need to do all this in complete darkness because these craters never see sunlight. That's challenging enough. But here's the real problem. We're not even sure how much water is there. Our data comes from orbital observations, spectroscopy, neutron detectors, radar, all of which suggest water is present. But we don't know the concentration. We don't know the depth. We don't know if it's easily accessible or locked in minerals that would require industrial processes to extract. We won't know until we send missions there to drill and sample. And those missions themselves are risky because of the extreme cold and difficult terrain. Let's say we do find accessible water. Great. Now you need to mine it. Bring it back to your base. Purify it. The mining requires energy. Lots of energy. The transport requires vehicles that can handle the temperature extremes between the permanently shadowed craters and the areas where your base would be located. The purification requires equipment and more energy. And remember, water is heavy. Even in 1/6 gravity, moving large quantities of water around is hard work. You can't just carry it in buckets. You need pumps, pipes, storage tanks. All of which need to survive the temperature swings, the vacuum, the radiation, the dust. But let's say you've solved all that. You've got water. Now you need to not waste it. Every drop is precious. On Earth, we use water for everything. Drinking, cooking, washing, toilets, agriculture. We waste it constantly and don't care because more is always available. On the moon, every molecule of water would need to be recycled. Your urine gets filtered and turned back into drinking water. Your sweat gets captured and recycled. The water you use to wash would be filtered and reused. You'd need near-perfect recycling efficiency because getting more water is expensive and difficult. The ISS does this now. They achieve about 93% water recycling efficiency, which sounds good until you realize that means they lose 7% of their water. They make up for this with regular resupply missions from Earth. On the moon, you couldn't rely on resupply missions. Too expensive. Too difficult. You'd need to be completely self-sufficient or very close to it. And what happens if your water recycling system breaks down? What if contamination gets into your water supply? What if you have a leak? Water loss on the moon could be catastrophic. People can only survive a few days without water. If your supply runs out and you can't get more, everyone dies. Simple as that. This creates psychological stress too. Imagine every time you wash your hands, you're thinking about water conservation. Every time you're thirsty, you're aware that this water is recycled from yesterday's urine. Every drop that spills is a potential emergency. That constant awareness, that constant need to conserve, would be mentally exhausting. Mars has an advantage here. While getting to Martian water would still be challenging, there's more of it, it's more widespread, and the temperatures, while cold, aren't as extreme. Extracting and processing Martian water would be difficult, but more straightforward than the moon. There's another aspect to water that people don't always think about. Radiation shielding. Water is an excellent radiation shield. It's dense, it absorbs particles, and it's non-toxic. On a space station or moon base, you could potentially line your habitat's walls with water tanks. This serves dual purposes. radiation protection and water storage. But this creates a vulnerability. If your water storage is damaged, you lose both your radiation shielding and your water supply simultaneously. One micrometeorite hit in the wrong place could be catastrophic. Your safety systems need to account for this. You need redundancy. Multiple separated water storage systems so that a single failure doesn't doom you. All of this complexity stems from the simple fact that water on the moon is scarce and hard to access. Every human activity requires water. Drinking. Hygiene. Food production if you're trying to grow crops. Oxygen production if you're electrolyzing water into hydrogen and oxygen. Rocket fuel production if you're trying to use lunar resources. Water is the foundation of everything. And on the moon, that foundation is shaky. Part 11. The communication problem we don't talk about here is something people don't usually consider. Communication. Specifically, continuous communication. On Earth, we're used to being able to communicate with anyone, anywhere, anytime. We have satellites. We have cell towers. We have the internet. On the moon, communication is more complicated than you might think. And in emergencies, this complication could be deadly. The moon rotates once per lunar month, which is about 28 Earth days. This means that any given spot on the moon faces away from Earth for about 2 weeks at a time. During that time, direct communication with Earth is impossible. You're on the far side. Radio signals can't penetrate through the moon. The Apollo missions dealt with this by simply not going to the far side. They stayed on the near side where Earth was always visible. They could always communicate. But if we're establishing a permanent presence on the moon, we need to explore the whole moon, including the far side. The far side has scientific value. It's shielded from Earth's radio noise, making it an ideal location for radio telescopes. Some of the permanently shadowed craters with water ice are on the far side. We need to go there. But anyone on the far side would be completely cut off from direct communication with Earth. You'd need relay satellites. Multiple relay satellites to ensure constant coverage. These satellites need to be maintained, powered, and positioned correctly. If they fail, you're isolated. Imagine being on a moon base and having an emergency. Your oxygen system is failing. You need help. You need advice from Earth. But you're on the far side and your relay satellite just failed. You're on your own. Completely on your own. For potentially hours until you rotate back to where you can see Earth directly or until the relay satellite can be repaired or replaced. On Mars, communication is delayed but not blocked. You can always send a signal to Earth and know it'll get there eventually. The delay is frustrating but predictable. You plan for it. You accept it. On the moon, you can have real-time communication most of the time, but complete communication blackouts part of the time. This is arguably worse because you become dependent on that real-time link. You start to rely on being able to call Earth when you need help. And then suddenly you can't. The psychological shock of that sudden isolation could be severe. There's another communication problem that's more subtle. The moon has no ionosphere. Earth's ionosphere reflects radio signals, allowing long-distance communication even over the horizon. You can send a radio signal from New York and have it bounce off the ionosphere to reach London. The moon has no such layer. Radio signals travel in straight lines. If there's a hill or crater wall between you and whoever you're trying to talk to, you can't communicate. Line of sight only. This means that rovers exploring the lunar surface could easily lose contact with their base if they go behind a crater rim or over a hill. You'd need to carefully plan routes to maintain communication. Or deploy communication relays as you go. More equipment. More things that can fail. More complexity. The Apollo astronauts experienced this. When they went behind the moon in lunar orbit, they were completely cut off from Earth for about 48 minutes each orbit. They described this as one of the most isolating experiences of the mission. Knowing that no one in the universe could hear them. That if something went wrong, they were entirely on their own. Now imagine that isolation lasting for 2 weeks instead of 48 minutes. That's what people on the lunar far side would experience if their communication systems failed. And here's something else. The moon's environment degrades electronics, as we've discussed. Radio equipment isn't immune. Transmitters and receivers need to survive temperature extremes, vacuum, radiation, and micrometeorite impacts. They need regular maintenance and replacement. If you're far from your base and your radio fails, you might not be able to call for help. On Earth, if you're lost in a desert and your radio fails, you can send up a signal flare. You can light a fire. You can create visible signals. On the moon, none of that works. No atmosphere means no smoke. Signal flares don't work in vacuum. Visual signals don't carry far because there's no atmospheric scattering of light. You're invisible unless someone is looking directly at you. This makes search and rescue operations much harder. If someone gets lost or stranded on the moon, finding them is incredibly difficult. No heat signature to track because of the extreme temperatures. No radio signal if their equipment is dead. No footprints in snow or tracks in mud. Just gray dust on gray rock. Mars has these problems too, but Mars's atmosphere allows for different communication methods. You could potentially use sound at close range. You could use atmospheric phenomena for signaling. You have more options. The moon gives you radio and visual sight. That's it. And both of those can be easily blocked or interrupted. Living on the moon means accepting that at any time, you might be completely cut off from help. From advice. From communication with other human beings. And that isolation could last for hours, days, or even weeks depending on where you are and what's failed. Part 12. The speed of disaster. Here's something that makes the moon uniquely terrifying compared to Mars. The speed at which things can go wrong. On Mars, disasters usually unfold over hours or days. A dust storm approaches over hours. You can see it coming. You have time to prepare. Supplies running low. You have weeks to figure out a solution. Equipment failing. You can often limp along while working on repairs. Mars gives you time. Not much time, but some time. Enough to think. Enough to plan. Enough to potentially contact Earth and get advice. The moon doesn't give you time. Suit puncture. You have seconds. Maybe a minute if you're lucky and the hole is small. That's it. By the time you've realized something's wrong, you might already be unconscious. Solar flare. From detection to radiation hitting the moon's surface. 8 minutes. That's how long it takes light to travel from the sun to the moon. 8 minutes to recognize the danger, get inside, and hope your shielding is adequate. If you're far from your habitat, you might not make it. Oxygen system failure. Depending on the size of your habitat and the number of people, you might have a few hours. But the symptoms of oxygen deprivation are insidious. By the time you realize you're in trouble, your judgment is already impaired. You might not be able to fix the problem because your brain isn't working right. Temperature control failure during lunar day. Your habitat starts heating up fast. No atmosphere means no convection cooling. Your equipment is designed to handle this, but if the cooling system fails, temperatures inside could become dangerous within hours. People can die from heat stroke quickly, and in a sealed environment where you can't escape the heat, the situation deteriorates rapidly. The vacuum, the radiation, the temperature extremes, they're all immediately lethal or rapidly deteriorating situations. There's no slow decline. No gradual worsening that gives you time to adapt. The moon's dangers are like a switch. Everything's fine. Now everything's deadly. Pick one. This creates massive stress for anyone living there. Every system, every piece of equipment, every suit seal is a single point of failure that could kill you within minutes or hours. You're constantly one malfunction away from death. Compare this to Mars. If your heating fails on Mars, it gets cold. Unpleasantly cold. Dangerously cold. But it takes time. Hours at least. You have time to fix it or to put on warmer clothes or to move to a different area. The thin atmosphere provides some insulation. If your oxygen system fails on Mars, you still have hours to fix it. The larger volume of atmosphere in a Mars base compared to the thin air outside means slower pressure changes. Mars is harsh, but it's not as instantly lethal as the moon. It gives you a fighting chance. Time to react. Time to adapt. Time to survive. The moon is unforgiving. It doesn't give second chances. Every mistake could be your last. Every malfunction could be catastrophic. And knowing this, living with this knowledge every single day, would be psychologically devastating. Imagine going to sleep every night knowing that a single equipment failure could kill you before you wake up. Imagine walking outside in your suit and knowing that one tear, one seal failure, one electrical problem means you have less than a minute to live. Imagine that every breath you take depends on machines working perfectly in an environment that's constantly trying to destroy those machines. That's life on the moon. And people are volunteering for this. They're excited about it. Because the moon represents humanity's future in space, our first step toward becoming a spacefaring civilization. But the price of that future is measured in constant vigilance, constant risk, and the acceptance that death is always just moments away. Part 13. Why are we going back? So with all these dangers, all these threats, all these ways the moon is trying to kill us, why are we planning to go back? Why would anyone volunteer for this? What's worth risking everything for? The answer is complex, but it comes down to a few key reasons. And understanding these reasons helps explain why, despite being more dangerous than Mars, the moon is humanity's next destination. First, proximity. The moon is 3 days away. Mars is 6 to 9 months away depending on orbital alignment. If something goes catastrophically wrong on the moon, you might be able to abort and come home. Emphasis on might. On Mars, you're committed. You're staying for the entire mission duration. Multiple years. If you get sick, if you hate it, if you have a personal emergency on Earth, you can't just come back. This proximity makes the moon a better testing ground. We can try things, fail, learn, and try again without waiting years between attempts. We can build experience and expertise faster than we could on Mars. Second, economics. Getting to the moon is much cheaper than getting to Mars. The fuel requirements are lower. The life support duration is shorter. The radiation shielding needs for the journey are less extreme. We can send more missions, more equipment, more supplies to the moon for the same cost as one Mars mission. This economic advantage means we can make mistakes on the moon without bankrupting the program. We can learn the hard lessons close to home before we risk everything on a Mars mission. Third, resources. The moon has resources we need. Water ice, as we've discussed. Helium, 3, a potential fusion fuel. Metals and minerals. If we can learn to extract and use these resources, the moon becomes a stepping stone. A place to refuel. A place to manufacture equipment. A place to launch missions to Mars and beyond without having to lift everything out of Earth's deep gravity well. The moon's low gravity is a disadvantage for human health but an advantage for launching spacecraft. Once you have infrastructure on the moon, leaving the moon is much easier than leaving Earth. You need less fuel. Less massive rockets. The moon could become a gateway to the solar system. Fourth, science. The moon is geologically dead, which means its surface preserves a record of the solar system's early history. Impact craters from billions of years ago are still there, unchanged. Studying them tells us about the formation of Earth and the other planets. The far side of the moon, shielded from Earth's radio noise, is the perfect place for radio telescopes that could help us answer fundamental questions about the universe. Fifth, and this is the hardest to quantify but perhaps the most important. Inspiration. Humans are explorers. We climb mountains because they're there. We cross oceans because we want to see what's on the other side. We push boundaries because that's what humans do. The moon represents possibility. It represents humanity's ability to overcome challenges and expand beyond our home planet. The Apollo missions inspired a generation of scientists and engineers. The return to the moon will inspire the next generation. And maybe, just maybe, learning to survive on the moon will teach us how to survive on Mars. And beyond.